Hi, I'm Andrew Macquarie. Today I'm presenting the paper Exploring the Use of Skeletal Tracking for Cheaper Motion Graphs and On-Set Decision Making in Free Viewpoint Video Production. It was written by myself and Anthony Steed, and we're both from University College London. So first of all, I wanted to talk a bit about what I mean by Free Viewpoint Video, or FVV. So FVV is filmed content that supports viewing with 6 degrees of freedom, meaning that if you move your head from side to side, you're still viewing the content perspective correct. And this makes it an ideal content creation tool for VR and AR because these headsets support viewing with 6 degrees of freedom. The two example images that you see here are Microsoft Mixed Reality Studios. The one on the left is in America, the one on the right is Dimension Studio, who are based in Wimbledon in London, who we film some content with. In both of these examples, you can see that there's a central character performance which is surrounded by lots of cameras all facing inwards, capturing the performance from multiple perspectives simultaneously. So then after the character performance, there's a very data-heavy 3D reconstruction step, which uses techniques like segmentation and depth from stereo to reconstruct the shape of the character performance for each frame in the video. And then this shape is then textured using data from the RGB cameras to get the surface appearance. So you get both the 3D shape and the appearance captured for every frame of the video. So the output of this process is an FEV avatar. These are 3D avatars with animated mesh geometry and a video texture. These examples here is some content that we captured with Dimension Studio. You can see on the left the textured version, and on the right you see the 3D geometry. And these are really very high quality. You can see that they're really approaching photorealism in this context. And our content, and as far as I'm aware, all commercially available FEV content, is temporally unstructured, meaning that the underlying mesh geometry changes completely every few frames. And this allows the avatars to be very flexible and represent rapidly changing shapes. So why do we think FEV is interesting? Well, there's a really big increase in the number of pieces of content that are using this technique. This is an example of a piece of content from 2017 from Blade Runner 2014 Memory Lab. And you can see the character on the left here has been volumetrically captured in an FEV studio. And a recent estimate said that there were now 51 commercial FEV studios worldwide, which is a massive growth within the last 5 years. And so because this content is captured from the real world, it means that there's no 3D modeling required. So it's much more much more similar to a video production type pipeline that a lot of people are going to be used to. And the content that you get out is in some ways more realistic than motion capture performances that are applied to rigged avatars. For example, you get things like the very realistic cloth dynamics because the surface appearance and dynamics have been captured. So although there's a lot of advantages to FEV content, there's also challenges. One of the biggest ones is cost. The 3D processing step, because it's so data intensive, is very expensive. So it costs around £6,000 per minute of rendered content at the moment. So that's about £100 per second just to perform the 3D processing. Also, the experiences can lack interactivity. Because they're fixed at the point of filming, like a video, they can't really interact with you and respond to user input in the way that you would expect from a rigged avatar, for example. And also there's a lack of feedback on set. Because the 3D processing can take days, you don't get on-set volumetric playback, so you can't necessarily tell if a shot has worked on set, which means that you might have to do expensive reshoots later on because you can't watch it back in the head-mounted display. So one way to address the cost issue is through content reuse. So for example, you could use motion loops where you process quite a short piece of content and then repeat it. So this is useful if you have, like for example, a walk cycle where the repetitive motion of the cycle means that you can loop back into the content in a way that it can easily be disguised. And one possible technique to address the lack of interactivity is through motion sequences. So this is where you stitch together chunks of motion. So for example, somebody running, somebody stopping, somebody turning, and you stitch those together at runtime so that the character can have interactivity. And in order for these to be believable, both the motion sequences and the motion loops, you need to find match points. So this is points at which the shape and the dynamics of the character are similar enough that the cut between the clips won't be discernible. And that's what this work is concerned with, that we're trying to find these match points between the different clips. In both cases, you're constructing a graph of different motion clips, where the cut between the different clips is where the frames appear most similar. And there's been a lot of previous work, some from Surrey and from Microsoft and from others, looking at how to identify these match points using the reconstructed meshes. And these produce really brilliant results. You get really excellent visual results from this. But the problem is that because they work on the 3D process meshes, it means that you need to have already done the 3D reconstruction step for all of the content that you want to compare. And that's the most expensive part, doing that reconstruction. So you're putting in a huge amount of effort up front for content that may not actually be used in the final output. So our idea was to try and avoid the 3D reconstruction step and perform comparisons before 3D reconstruction, because that's what makes it so expensive. So the idea was to use skeletons. Because these studios tend to use structured infrared light already, it means that you can't use off-the-shelf depth sensors like the Kinect, for example. And also because the capture captures the surface appearance, it also means that you can't place markers on the actor. So instead we decided to try and use OpenPose, which is an open source framework which can identify skeletons in RGB images. And the questions we were really trying to ask here were, can skeletons, which are tracked via OpenPose, actually even work in this context? Can they be used to identify match points? And if so, what can they be used for? Might it be possible to use them on set, for example, to assess if you've captured the right content and therefore avoid having to do expensive reshoots? So this is how our skeleton-based match point detector system works. The input is an RGB image for each frame from each of the cameras in the rig. In our case, there are around 50 RGB cameras in the rig. We then use OpenPose to detect the 2D skeleton in each of those images. Because OpenPose works in 2D, we then need to lift it into the 3D world, which we do by using multi-view geometry. Because we have the camera calibrations for each of the cameras, we can work out where the rays for each joint intersect, and that becomes that joint's 3D location in space. We then perform the skeleton comparisons. In order to do that, we align the skeletons in a least squares sense, and then we calculate the distance between all the joints, and we take that to be the difference between those two frames. We include all the specifics of how this works in the paper, so if you want to see the details, then have a look at the paper. Okay, so now I'm going to talk about how we went about evaluating our system and what results we got. So as I mentioned before, the output from FAV Studios at the moment is avatars where the meshes are temporally unstructured, meaning that the mesh changes every few frames. And that creates problems for assessing our system because it's really difficult to get a ground truth value for how similar the frames are to each other from real world data. If the frames were temporally consistent, if the mesh was consistent, then we could do it in a relatively easy way. We just align the skeletons and then compare the distances of the vertices from each other, because each vertex would have a corresponding vertex to check against. But because it's unstructured, we can't do that. So we can't get a ground truth from the real world data. So instead, what we do is we follow the examples in the literature, and we create a synthetic data set. In order to do that, we reconstructed the layout of the rig in Blender. So we took the camera calibrations from a real world shoot and applied them to lots of virtual cameras inside Blender 3D, a 3D software package. And then we apply a motion capture performance to a rigged avatar and drive that avatar through several motions, like walking and stopping and running and such. And then we generate an output from that, which is very similar to the type of input that we would get to our system in the real world. So by that I mean we get a single RGB image for each frame from each camera for every camera in the rig. And so we have that, but we also have the ground truth. Because the avatar has a known and fixed geometry, because it's a rigged avatar, then we can compare each frame against each other by aligning the avatars and comparing the distances between the vertices. To look at how accurately our system is performing, we can use heat maps to get a visual indication. So here you see some heat maps. Each of these heat maps represents a self-similarity. So this is when we compare each frame in a clip against every other frame in the same clip. So this is why they're square. So each pixel in each of these images, so say you take the XY pixel, that's comparing frame X against frame Y in that clip. So you'll notice that there's very strong diagonal lines running from the top left to the bottom right, and that's exactly what you would expect, because for each of those pixels, that's comparing the frame against itself. So in these heat maps, a very dark pixel indicates that the frames are more similar, and brighter pixels mean that they're less similar. And on the top, you'll notice that is the ground truth. These are the ground truth values, and the images below are the heat maps generated by our system. And you'll notice that the shape is very similar. We're really seeing a very similar shape between these two heat maps, indicating that our system is really working as you would expect. To analyze the system statistically, we used the same process that the other people have used in the literature. So we looked at receiver operating characteristic curves. So this is what you see on the right here. And these curves are really an indication of, as you make a discriminator more sensitive, to what extent does it damage the specificity? So to read these graphs, ideally what you want to see is a line that goes straight up the left-hand side, the left-hand axis, and then straight across the top axis. That would mean that it's an ideal discriminator. So really what you're wanting to see is a curve that gets as far into the top left-hand corner as possible. And you can see here from these lines that our discriminator is performing really well. The lines are really right up in the top left-hand corner. Comparing our system against the state of the art, we found that we were around 2.8% less accurate. This is sort of as you would expect, because the other systems have access to the fully processed 3D mesh. They have more information available to make their comparisons. So we were expecting a small drop in accuracy. But our system is substantially cheaper. Our comparisons can be done before 3D processing, so the final cost of our system is linked to the amount of content you need for the final output rather than the amount of content that you want to compare. This cost saving can be really, really high, but in an example that we give in the paper, we were talking around a 6.2-fold decrease in costs for our system versus the state of the art. We also did an evaluation on real-world data. Because we couldn't get a ground truth for this data, we instead present it as examples. And the example that you see here on the right, it shows that our skeleton-based match point detector system will output a score, and that score is an indication of how similar those frames are. So on the left-hand side, you see these two meshes where the blue and the green mesh are from separate shots. The one on the left is clearly more different than the two meshes on the right, and this is reflected in the score that was given by our system. So the left one got a score of 67, while the one on the right got a score of 34. Just to mention that a higher score is a worse result because these represent the distance between the joints for that take. In the paper, we also explore the possibility of using the system on set and to what extent we think it could work in near real time. And this would be really useful. So as an example, in the shots that we filmed, it's actually very difficult to cut from the walking clip to a stop walking clip, because in all of the shots we filmed, in the stop walking clip, the actor is leaning very slightly backwards. So actually there isn't a great cut between those two shots. So if we had had this system available on set and it had given us a score that showed that there wasn't going to be a good cut, then we could have immediately refilmed those takes. Additionally, if you had this system on set, then you could use that to drive rigged avatars, and then you'd be able to get some degree of playback. So just to sum that up, we looked at using 3D skeletons to assess match point quality in free viewpoint video. We found we had an accuracy that was slightly below the state of the art, but with a substantial cost saving. We also explored whether or not we could use the system on set in near real time to assess if we needed to do reshoots based on match point quality, and also potentially to drive rigged avatars for on-set visualization. Okay, thanks very much.